Okay, so I am back after a very extended hiatus. Freshman year got a little busier than I thought it was gonna be, but yeah, I'm excited to be back. And this year, at least for now, I plan to cover more organic chemistry, as I think it'll help me study for the exams better by forcing me to review and explain each reaction mechanism, because believe me, there are a lot. But today we're going to be covering the Gringard reagent. Now, essentially, all the Gringard reagent is a metal attached to a halogenated carbon. So I forget the name of those, but basically, if we just have a simple carbon here with a halogen, what we can do is note that this carbon is currently positively charged. But if we react magnesium in an ether solvent, essentially the magnesium is going to insert itself in between the halogen and the carbon it's connected to, which produces this compound right here. Why is this important? Well, essentially, the magnesium has a lower electronegativity than carbon, which means this carbon is now negatively charged. And you can do this with lithium as well. Lithium and ether, you'll get essentially the same thing. You'll get basically the same thing. It does the same thing. It makes that carbon negative, but because there's two lithium ions, it actually fully pulls off the bromine, so you just have a Li-Br complex attached to that. Now, like I said, this is important because it makes this carbon negatively charged. Essentially, the carbon in a Gringard reagent now becomes the nucleophile, which is great when reacting it with ketones, because it now means basically we can add a carbon chain to certain ketones. So, one more important thing too, this reaction must be dry, which means no water at all. Like my professor was saying, even moisture in the air can cause a problem with this. You can't have acids or really anything that can lose a proton or has a acidic proton. So the reason for that is because essentially what will happen is, let's say we have water. Essentially what's going to happen is it's just going to protonate. So basically the Li gets kicked off and the proton attaches to that carbon, and then you just have, like, all this is just a CH3 bonded to a CH3, which isn't very reactive. Now, like I said, the reason Gringard reagents are important is because the carbon now becomes the nucleophile, which means that we can react with things like ketones. So in this example I have set up here, we have a magnesium bromine, and again, this carbon is negatively charged, reacting with a pretty simple ketone. Now, note that the reason this reaction happens is actually due to resonance. So another resonance structure of this ketone is this guy right here, where the oxygen atom is negatively charged, this carbon is positively charged. So essentially what happens is this electronegative carbon is going to attack this ketone, and these electrons are going to go to the oxygen because, again, this resonance structure, this carbon is partially charged or partially positively charged. So this negative is going to attack this positive, and it will produce something similar to this. I'm not sure if that's a backside attack. My professor didn't talk too much about that, it'll look like this. Forgot the extra carbon there. But yeah, so basically that's it. It's really not a too difficult reaction. And then again, if we have H2O here, if we have a water workup at the end, that O just gets protonated and we end up with a alcohol. And yeah, they're really not too terribly difficult reactions. I have a second one here, this time with an epoxide. They're also useful for reacting with epoxides. Really anything, they're really nice because they allow you to add carbons to carbons with, of course, certain reaction groups. So in this case, we have a phenol, which is just a benzene ring. With a magnesium bromide attached to it. So again, this carbon is going to have a partial negative. And when we react it with this epoxide here, what happens is these electrons go there, this partial attacks this side. Now, this is important to note. Even though technically this partial carbocation is more stable, it's also more sterically hindered than this side, right? And with a big molecule like this, or really in most examples I've seen so far, this steric hindrance is enough to cause, it basically offsets the preferred carbocation. It actually completely does, because not completely, but as far as I'm aware and as far as I've seen, this partial negative will not attach to this carbon atom here. So essentially what that results in is you end up with something that looks like this. And then you have your phenol group here. Plus your magnesium bromine counter ion. But yeah, like I said, it's important to note that there's just two hydrogens here, so this carbon is still happy, and there's a hydrogen here as well. But yeah, like I said, because of the steric hindrance here, the phenol group can't really fit in there without being blocked by that methyl group there. So it will attach to the other side, and then again, if there's a water workup or acid or anything that can donate a proton, it will just form that into an alcohol. Yeah, so I have one more example. Now, these are copper complexes, which are a little bit different. I don't technically know if they're Gringard reagents, but they behave pretty similarly. So, for example, let's say we start with a propene connected to a bromine, and we react that with lithium to give us that right there. And now if we react this, don't forget this counter ion. Now if we react this with, I think that's cupric iodide, could be wrong. But if we react it with copper and iodine, that will actually produce this complex right here. Now, it's important to note that this copper actually has two of these groups attached to it. So, for example, if we react this with I don't even know the name of that. If we react it with I'll just draw it. What this kind of looks like here is something along the lines of that. It just has two of these groups sticking off of it. If we react this with this guy right here, of course, keep in mind it's an ether solvent. We will actually end up with now Cl will go here. Note again, the electronegativity is what causes this. That has a partial charge. This is a partial negative. So essentially, this partial negative right here comes in and attacks this. And what we end up with is this guy right here, plus, keep in mind that this had two on it, so we actually end up with this, that lithium pops off and acts as a counter ion for the chlorine. So again, another pretty simple reaction. If this is a Gringard reagent, I apologize because his notes, my professor is a little disorganized, but he gives a ton of examples, which I'm grateful for because it helps me understand. But yeah, this behaves very similarly to a Gringard reagent. Obviously minor differences, but yeah. So, and like I said, Gringard reagents are pretty simple. They're not terribly difficult. I want to do this just more so for review. I plan on doing some OChem 1 topics as well. But I'll just have to get to those when I get to those, namely like nucleophilicity and SN1, SN2, E1, E2, all of those more confusing and difficult types of reactions. But for now, at the end of this video, real quick, I do want to cover carbenes because they will set us up for Wittig reactions later on, and that's a big one. I think that'll probably have a video all for itself, but hopefully coming later this week, but we'll see about that. Carbenes are pretty simple. Basically all they are, there's no apostrophe there. I don't know why I did that. Basically all they are is just a negatively charged carbon with free electron groups. But yeah, so there's a couple ways that we can form these. He didn't talk too much about these, more so just leading into the Wittig reaction. Now, if we have this right here, these nitrogens are a very good leaving group, and all it takes he didn't really explain that HV. I assume high voltage or light or energy or heat or something of some excess energy of some kind. That group will actually pop off and you'll be left with your carbene right here. Similarly, if we have this compound right here, I guess it's a little different, and you react it with tert butoxide, that H actually gets pulled off by this strong base here, and we end up with the earth. We end up with this compound right here, which negatively charged, and we actually, a bromine will pop off, and we end up with this carbene right here. Now, I'm not too sure of the mechanisms for these. Like I said, he didn't spend too much time on them, but I did just want to quick review them, and I'll probably review them a little more after this video too, and just really look into these some more. Though I think they're more so important to understand just for Wittig reactions and Wittig reagents, which, like I said, are coming soon. But essentially, oh, this is a neat property about carbenes, actually. When you react them with a alkene, you actually get a cyclopropane. Yes, you end up with a cyclopropane, end up with a cyclopropane. Actually, it is, though, important to note that stereochemistry is retained. So if we react this carbene here with, we can use one of two. Now let's say we react with this guy, or this guy right here. If we react it with this guy, our cyclopropene will look something like this, or actually this, it will be a racemic mixture between these two guys right here, which I actually I think actually these guys are the same compound. There's no difference between the two. So essentially stereochemistry will be retained. And sort of a similar thing happens here, except the two carbons will be on the trans position. But yeah, that is about all I want to cover in this video. Like I said, we're doing Wittig reactions sooner or later, hopefully by the end of this week. Probably not. If not, the end of this weekend, and I might do 2 videos this weekend just because I'll have a lot of free time. But yeah, I'm excited to get back to making these videos because they help me study a lot and force me to do some review, and just kind of talking through it sometimes helps. But yeah, on to the next.